In this lecture video, we're going to see how to analyze data from a complete factorial treatment structure. In particular, we're going to see how to perform an analysis of variance and construct the analysis of variance table when we have a complete factorial treatment structure. So let's first look at the general approach that we're going to use in performing an analysis of variance and constructing the ANOVA table when we have a complete factorial treatment structure. So this is the set of steps that we're going to use in performing the analysis of variance in this context. The first step is to construct the ANOVA table for the design structure used in the experiment. For example, it could have been a completely randomized design, a randomized complete block design, or perhaps a Latin square design. And we do this treating the treatment structure as a one-way treatment structure. Now, the reason we're going to do this as the first step is because we already know how to perform an analysis of variance and construct the ANOVA table when we have a one-way treatment structure. So that's going to be the starting point for the analysis of variance in this situation where we have a factorial treatment structure. Now remember that the structure of the ANOVA table corresponds to the structure of the statistical model. And so when we perform the analysis of variance and construct the corresponding ANOVA table, because we are treating the treatment structure as a one-way treatment structure, we're going to have the basic or condensed ANOVA tables because they correspond to that particular type of treatment structure. So let's look at some examples of condensed ANOVA tables for one-way treatment structures. And these are the ANOVA tables that we looked at in previous modules. So here is the basic or condensed ANOVA table for a one-way treatment structure when the design structure is a completely randomized design. Now notice in the header, I've got the means model representation of the statistical model for this situation. We have one parameter in the model for the treatment means. That parameter is mu sub ij. And we have one line in the ANOVA table that corresponds to that source of variation. Then in the model we have an error term, the epsilon ijk's, and corresponding to that we have a row in the ANOVA table for the error source of variation. And then finally, the bottom row in this ANOVA table is the total source of variation, and that corresponds to the left-hand side of our model, the yijk. So here we see that the structure of the ANOVA table corresponds to or mirrors the structure of the statistical model. Now notice that in this particular table, this is the format that we used before, where we use T as the total number of treatments. Now in this particular section, we are being a little bit more specialized in that when we first looked at the completely randomized design, we allowed the number of reps to vary from one treatment to another. But in this particular section, we're going to be looking at balanced models or balanced treatment structures where we have the same number of reps per treatment combination. And so we're going to denote that common number of replications per treatment combination by R, and that is represented in this table. Next, we have the basic or condensed ANOVA table for the one-way treatment structure when we have a randomized complete block design structure. Again, notice that I have the means model representation for the model, y sub ijk equal to mu sub ij plus rho sub k plus epsilon ijk. Now, in the ANOVA table, the first row corresponds to the blocks as a source of variation. That corresponds to the rho sub k's in my model. The second row is the treatments as a source of variation, and that corresponds to the mu sub ij in the model. The third row in the ANOVA table is the error source of variation, and that obviously corresponds to the epsilon ijk, the error term in the model. And then finally, the fourth row in the table, the total variation, that corresponds to the left side of the model, the Yijk. And so again, we see that the structure of the ANOVA table corresponds to the structure of the model. And then finally, we have the basic or condensed ANOVA table for the one-way treatment structure when the design structure is the Latin square design. Now, in this particular table, we're using the same notation that we used back in the module on the Latin square design. In particular, P is the number of treatments, and so that's reflected in those formulas for the degrees of freedom. Now, notice again that I have the means model representation of the statistical model. The first row in the ANOVA table is the source of variation for the rows in the Latin square, and that corresponds to the row sub I in the model. The second row in the ANOVA table is for the columns in the Latin square as a source of variation, and that corresponds to the gamma sub j in the model. The third row is the treatments as a source of variation, and again that corresponds to the mu sub k in the model. And then finally, we have the error source of variation in the ANOVA table, and that corresponds to the error term, the epsilon ij in the model. And then finally, the last row on the table, that's our total source of variation, and that corresponds to the left-hand side of the model, the Yijk. And so again, we see in this example as well that the structure of the ANOVA table corresponds to the structure of the statistical model. And we're going to see that that continues as we continue this process of performing the analysis of variance. So that was step one. Construct the ANOVA table for the design structure used in the experiment, treating the treatment structure as a one-way treatment structure. Now, when we do that, we're going to, and let me go back to one of these slides here. Let's say that we're talking about the completely randomized design. And so when we construct that basic or condensed ANOVA table, where we consider the treatment structure as a one-way treatment structure, we're going to have all of these values computed and put into the table. We're going to have the degrees of freedom entered. We're going to have the various sums of squares calculated and entered. From these sums of squares and degrees of freedom, we will be able to calculate the mean squares. And then once we have the mean squares, we can calculate the F statistic. But in particular, we're going to have the value of SST, the treatment sum of squares. And that is going to be the case regardless of whether we're talking about a completely randomized design, a randomized complete block design, or a Latin square design, or maybe some other design that we haven't talked about yet. So with that in mind, the next step is to partition the treatment sum of squares, that value of SST that we obtained in step one when we performed the ANOVA for, or considering the treatment structure as a one-way treatment structure. We obtained SST in that step, and so in step two we're going to partition the treatment sum of squares and do that partitioning according to the particular complete factorial treatment structure that was used in the experiment. Now, let me just say that this general approach is going to work regardless of the number of factors that we have comprising that complete factorial treatment structure. In the examples and in the demonstration that I'm going to show you, we're going to focus on a two-factor complete factorial treatment structure. But this general approach will work regardless of the number of factors. So let's look at how to partition the treatment sum of squares, the SST value that is computed as part of step one. And like I said, we're going to do this specifically for a two-factor complete factorial treatment structure. And so we're going to be partitioning the treatment degrees of freedom and the treatment sum of squares. And so for a two-factor complete factorial treatment structure, this is how we do that. So to partition the treatment degrees of freedom, for a two-factor complete factorial treatment structure, the number of treatment combinations is A times B. The number of degrees of freedom associated with treatments is therefore A times B minus 1. And we are going to partition the treatment degrees of freedom into three separate components. The degrees of freedom associated with factor A, the degrees of freedom associated with factor B, and finally the degrees of freedom associated with the interaction of factors A and B. And so the number of degrees of freedom associated with factor A is A minus 1. The number of degrees of freedom associated with factor B is B minus 1. And then the number of degrees of freedom associated with the interaction of A and B is A minus 1 times the quantity B minus 1. Now, it may not be obvious that those three numbers add up to A times B minus 1, but if you expand the binomial on the right-hand side and add those up, you'll see that that is indeed the case. Now, along with partitioning the treatment degrees of freedom, we're going to partition the treatment sum of squares. And so we have SST, we computed that in the first step. And what we're going to do is to partition that treatment sum of squares into three components. The sum of squares due to factor A, the sum of squares associated with factor B, and the sum of squares that correspond to the interaction of A and B. All right, and those three components are denoted SSA, SSB, and SSAB, respectively. Now, once we have partitioned the treatment sum of squares into those three components, SSA, SSB, and SSAB, and we have the corresponding partitioning of the degrees of freedom, we can calculate mean squares by dividing the sum of squares by their corresponding degrees of freedom. And then once we have the mean squares, we can calculate F statistics for testing the significance of the following effects. We'll be able to test the significance of the A-B interaction. We'll be able to test the significance of the main effect of A. And we'll be able to test the significance of the main effect of B. All right, so here is the treatment structure portion of the ANOVA table. Now notice that this is not a complete ANOVA table because I don't have a row for the error as a source of variation. I don't have a row for the total source of variation. What I've done here is I've extracted from any one of those three basic ANOVA tables that we looked at previously. I've extracted the row for treatments, which has A times B minus 1 degrees of freedom. And I've expanded the table to correspond to the effects model representation for the treatment means that I have listed up in the header. So notice that I have on the left-hand side of that equation, I have the means model representation for the treatment means, mu sub ij. And on the right-hand side, I have the effects model representation, mu plus alpha sub I plus beta j plus alpha beta ij. Now, the mu sub ij, that corresponds to the treatments row, all right, the overall treatments row. And then the alpha sub I in the effects model representation corresponds to the row for the effect of factor A, or the variation due to factor A. Beta j corresponds to the row for factor B, and then alpha beta sub ij corresponds to the row for the A-B interaction. So again, we can see that the structure of how we're representing the treatment means, that corresponds to this expanded version of the treatment portion of the ANOVA table. Now notice that in the sum of squares column, I have the notation for the sum of squares for the A main effect, the B main effect, and the AB interaction effect. I have those positioned on the right-hand side. And this is just, I do this just as a visual reminder that these quantities comprise a partitioning of SST, and so they are going to add up to that SST value. Similarly, I've done the same kind of formatting or arranging in the degrees of freedom column. The number of degrees of freedom associated with treatments is A times B minus 1. And then I have the degrees of freedom for A, the degrees of freedom for B, and the degrees of freedom for the interaction of A with B in those cells, right justified, again, to help us remember that those numbers comprise a partitioning of the treatment degrees of freedom, and so therefore they will add up to the treatment degrees of freedom, which is A times B minus 1. All right, so now let's look at how to calculate the quantities that are going to be needed to partition the treatment sum of squares, SST. And so the first thing we're going to do is to calculate the response totals, the T sub ij's, and the uncorrected sum of squares, which we will denote by USS sub ij, for each of the A times B treatment combinations. So again, this is a two-factor complete factorial. The total number of treatment combinations is A times B. And so for each of those treatment combinations, we're going to calculate the total of the responses for that treatment combination. That's represented by T sub ij. And we can also represent that, as you can see here, as Y sub ij dot. All right, remember that the dot notation means that we're summing over that third index or third subscript. And so that's expressed more explicitly in that far right-hand side expression. The sum of the Y sub ijk's, where k goes from 1 to r. And then we also need, for each treatment combination, for the ijth treatment combination, we need the uncorrected sum of squares, which we're going to denote by USS sub ij. And that's equal to the sum of the squared observations, the square of yijk. We're summing those up, k going from 1 to r. And it's convenient to organize these two sets of sums in separate two-way tables with a cell for each treatment combination and marginal cells for row and column totals, as shown on the following two slides. So in this table, the rows correspond to the levels of factor A, the columns correspond to the levels of factor B. In the body of the table, in the ijth cell, so the intersection of the ith row and the jth column, I have T sub ij. So that corresponds to the total for the observations at that treatment combination. Notice also that I have an extra row at the bottom for column totals and an extra column on the right-hand side for row totals. Here is the two-way table of treatment combination uncorrected sum of squares. And again, the rows correspond to the levels of factor A. The columns correspond to the levels of factor B. In the ijth cell, I have the uncorrected sum of squares for the observations that have received treatment combination ij. And as in the previous table, I have a row at the bottom for calculating column totals and a column on the right-hand side for calculating row totals. Now, once I have those quantities, we're going to use them to calculate the factor totals and the overall grand total, and also the sums of the uncorrected sum of squares. So let's start by looking at calculating the factor totals and the overall grand total. So the totals for levels of factor A are denoted by A sub I going from 1 to A, little a. And so A sub I is the total for level I of factor A. And this is obtained by summing up the T sub ij's, j going from 1 to B. We also calculate the totals for the levels of factor B. So these are denoted by capital B sub j. j going from 1 up to little b. And these are obtained by summing up the Tij's with respect to the first index, I. So I going from 1 to a. And then once we have those, we can use them to calculate the overall grand total, which we denote by capital G. And we can get G by summing up the a sub i's, I going from 1 to a, or by summing up the b sub j's, j going from 1 to b. We could also get capital G, the grand total, by summing up the Tij's over both indices, I going from 1 to a, j going from 1 to b. Or we could also represent this using the y notation as y sub dot dot dot, where that again means that we are summing up the y values over all three subscripts. Now, the notation here, that it looks a little cumbersome. We've got these summations all over the place, but they're easily performed and conveniently organized as row and column totals in the two-way table of treatment combination totals that we looked at before, and as I'm going to show you on the next slide. Let me just point out that the row totals and the column totals both add up to the grand total G, and so we have two ways of calculating G, and that gives us a nice convenient quality control check on our calculations. And so here we have that two-way table of treatment combination totals. And so what I've done is calculated the column totals. Those are the b sub j's. I've also calculated the row totals. Those are the a sub i's. And then we can get the overall total G by either adding up the a sub i's or adding up the b sub j's. And it's a good idea to do that summation both ways, just to make sure we get the same value. Again, that's a good quality control check to have. All right, similar to that, we calculate the uncorrected total sum of squares. And so we calculate the uncorrected sum of squares for factor A, the USS I dots, and we obtain that for each value of I, each level of I, by summing up USS IJ from j going from 1 to b. We also calculate the uncorrected sum of squares for factor B, USS.j, and that's obtained by summing up the USS IJs over the first index, I going from 1 to a. And then once we have those, we can use those to calculate the uncorrected total sum of squares, USS tot. I can obtain USS tot by summing up either the USS I dots, I going from 1 to a, or the USS.j's, j going from 1 to b, or I can just add up all of the USS IJs over both subscripts, I and j. And finally, just to help us remember what this represents, we could also calculate it as the square, as the sum over all observations in the data set where we're summing the squared values. So we square each observation in the data set and then add those up. So we're going to need these. We're going to need, in particular, the uncorrected total sum of squares. These calculations are easily performed and conveniently organized as row and column totals in the two-way table of treatment combination uncorrected sum of squares, as shown on the following slide. And again, let me just point out that the row totals and the column totals both add up to the uncorrected total sum of squares, USST, and it's good practice to calculate both of those sums to make sure we get the same value, because that gives us a convenient quality control check on our calculations. And so here is what that looks like, this two-way table of treatment combination uncorrected sum of squares. Ultimately, what we're after here is the bottom right corner, the USS tot, the uncorrected sum of squares total. All right. Now, those could be used in performing the calculations for constructing the basic or condensed ANOVA table. All right. So there is some overlap between these calculations and the calculations that you would have already done. But we do need these a sub i's and the b sub j's in this process of partitioning the treatment sum of squares. And so let's see how we do that. So again, in constructing the basic or condensed ANOVA table, we would have already calculated the treatment sum of squares. We would have already calculated SST. And so that is a known quantity. That's the quantity that we're going to be partitioning. So the next calculation we need to make is to calculate SSA, the sum of squares for factor A. And that's calculated from the A sub i's as 1 over R times B, R being the common number of replications per treatment combination. B is the number of levels of factor B. We multiply that by the sum, I going from 1 up to little a, of the square of the A sub i's. Once we have that, we subtract from it C, which you'll recall is the correction factor. And you will have already calculated that because you have already constructed the basic or condensed ANOVA table, and you need that correction factor C in performing those calculations. And so you already know how to calculate that. I'm not going to include that formula here, but you'll recall that it is the square of G, the square of the grand total, divided by the total number of observations. All right, next we calculate the sum of squares for factor B, SSB. That's equal to 1 over R times A, little a being the number of levels of factor A. We multiply that by the sum, J going from 1 to little b, of the square of the B sub J values. And then once we have that, we again subtract the correction factor C. Now, once we have SSA and SSB, and you'll recall that we already have SST because we've already constructed the basic ANOVA table. All right, then we have 3 of the 4 unknowns in that first equation. And so we have one equation with one unknown, the remaining unknown being SSAB, the sum of squares due to the interaction of A with B. And so we can solve that equation to get an equation for the interaction sum of squares, SSB, by subtracting SSA and SSB from SST, the treatment sum of squares. So that is how we partition the treatment sum of squares, and we do that according to, in this case, the 2-factor complete factorial treatment structure that we're using in this particular situation. Now, the next 3 steps we're going to group together. All right, we're going to expand the ANOVA table to include 1 row for each sum of squares comprising the partition of the treatment sum of squares. We're going to enter the sums of squares for that partition into the corresponding cells, and we're also going to enter the degrees of freedom for each partition component sum of squares. Once we've expanded the table and included the sum of squares and their degrees of freedom, then we can compute the mean square for each component of that partition. All right, so in doing this, we're going to be expanding the initial ANOVA tables that we constructed. We're going to be taking those basic or condensed ANOVA tables that were constructed assuming or treating the treatment structure as a one-way treatment structure, and we're going to expand them into ANOVA tables that take into account the 2-factor complete factorial structure of our treatment structure. And as we do this, what I want you to keep in mind is this fact that we talked about before, that the structure of the ANOVA table corresponds to the structure of the statistical model. And so let's look at the case for the completely randomized design. So here is the basic ANOVA table that we looked at before for a one-way treatment structure, and this treats the treatment structure as a one-way treatment structure. And so because of that, we have 1 row for the treatment source of variation. But now if we replace mu sub ij with the effects model representation for the treatment means, as we've done here, then we have the effects model parameters in this model, alpha sub I, beta sub j, and then alpha beta ij. And we have expanded the ANOVA table by including rows in the treatment portion of the table, one row for each of the effects model parameters in that model. So we have a row for the A factor, the A main effect, that corresponds to the alpha sub I in the model. We have a row for the B main effect, that corresponds to the beta j in the model. And we have a row for the interaction between A and B, and that corresponds to the alpha beta sub ij in the model. So the structure of the ANOVA table matches the structure of the statistical model. Similarly, we have the basic ANOVA table for a one-way treatment structure for the randomized complete block design. In the model, we have this is the means model representation for the model. And so we have one row for the treatment source of variation. But if we replace the means model notation with the effects model notation, then we have the effects model representation for the model. And then corresponding to that, we've added 3 new rows to the treatment structure section of the ANOVA table. So again, we have a row for the A main effect that corresponds to A or alpha sub I. We have a row for the B main effect that corresponds to beta sub j. And associated or corresponding to the alpha beta ij in the model, we have a row for the AB interaction source of variation. And then finally, we have the basic ANOVA table for the one-way treatment structure for the Latin square design, and the means model representation for that model here in the header, and the means model notation for the treatment comment, or for the treatment mean, is mu sub k. We have that one parameter, and so we have one row in the ANOVA table for the treatment source of variation. But when we expand it, we have 3 rows, one row for the A main effect, one row for the B main effect, and one row for the AB interaction effect. Now, in the model, I have not replaced the means model representation with effects model representation because it's a little bit cumbersome in getting the subscripting right. There's a little bit of a clash with the existing subscript, so I'm not going to include that. But we see how we do this. We expand the ANOVA table to account for the factorial sources of variation comprising that factorial treatment structure. So in each of these cases, all right, again, let's start here with the completely randomized design. We see that the ANOVA table, the structure of the ANOVA table, corresponds to the structure of the model. When we represent the model as using the means model representation, we have that single row for treatments in the ANOVA table. But if we think of the model and if we represent it as an effects model, then we can expand that ANOVA table to include those sources of variation. And it doesn't depend on the design structure. We do the same thing. That treatment structure portion of the ANOVA table is independent of the design structure part of the model and the design structure part of the table. So we have the same thing if we're talking about the completely randomized design or the randomized complete block design. All right, when we use the effects model representation of the model, we expand that ANOVA table. As well as the Latin square design, if we think about it as a one-way treatment structure, we have one row in the ANOVA table, but if we think about it in terms of the effects model representation and the different factors and their interaction, then we can add these 3 rows as well. All right, now the last step in the process is to determine appropriate F statistics for testing hypotheses of interest based on the expected values of the mean squares. Now, what do I mean when I say determine appropriate F statistics? Well, what I mean by that is we want to construct F statistics that test the hypotheses that we're actually interested in. Let me go back to, let's say the completely randomized design where we have the expanded ANOVA table. And notice that we have multiple F statistics. Let's look at the mean squares first. We know how to calculate mean squares. To get a particular mean square, we divide the sums of squares for that effect, and we divide by the degrees of freedom. So to get the mean square for treatments, we divide the sum of squares for treatments by its degrees of freedom, a times b minus 1. To get the mean square for A, we divide the sum of squares for A by its degrees of freedom, a minus 1, and so forth. Notice that in the F column, we have multiple F statistics. So we have F sub t, that is the F test statistic for testing the overall significance of treatments. We know how to calculate that. We would have calculated that in that basic or condensed ANOVA table. We also have F sub A, that is the test statistic for testing the significance of the A main effect. We have F sub B, which is the test statistic for testing the significance of the B main effect. And finally, we have F sub AB, that is the test statistic for testing the significance of the AB interaction. But notice that I've not included formulas for these test statistics. The reason for that is because in order to get those test statistics correct, we need to know, number one, what hypotheses we're interested in testing, and then we need to construct those F statistics in a manner that's going to help us to answer those questions, and we do that by constructing those test statistics based on the expected values of the mean squares. That is going to be the topic of the next lecture video, and so I'll see you there.